Welcome back this week, guys. Today we're going to be starting one of the, I would say, more difficult sections of the year that we're going to have. Um, so, with that being said, I expect if you guys do have questions, please let me know because, like I said, this is going to be a lot of information, some new ideas as far as how we use the information that we've already learned, but nothing real new, just manipulation of all the principles we've learned so far. So the idea behind filters is we can use these filters to filter out different specific signals that we want based on their frequency. At least that's how we're going to do these ones. There's other types of filters, but these ones are specific to the frequency of the signal that's coming in. So these are good for like audio applications. This is where we would take and filter out the low signals, the basses. Then you have your mids, your highs. We would filter all those out, and we're going to attenuate them. So if anything that doesn't conform to the parameters that we want it to be, whether it be a high filter, low filter, things like that, if we want a specific range, we can do that with these components. And all we use is with capacitors and inductors in just different configurations. And so we'll go over a little bit more about how those are going to work and the configurations that we have to achieve those, and kind of the idea of, okay, I want to create this type of a filter. I have these components. How do I do it? So we'll kind of go with that. So to kind of start with, we're going to go over some terminology, some basic ideas, some formulas that we're going to use, and then we'll get into determining what is an actual filter. Like what are we looking for? What are we calling filtered? What are we calling attenuated? Things like that. Then we'll go through each of the definitions of the filters that we have, some things to remember, and then we'll start it in with going on how to build filters. And so the idea here is we're going to go through RC filters, we're going to go through RL filters, we're going to go through a couple of design problems to kind of get you guys familiar with like, okay, I want to achieve this desired result. How do I do it? And then after that, the next topic that we're going to have is going to be once we get through the RC RL filters, we're going to get into another style of filter. We're getting into resonance filters, tank circuits, things like that, where that's what their whole job is these are actually kind of cool. The lighter set, um, instead of just allowing frequencies of higher than a certain value to go through or lower, whatever it may be, now we're actually setting up to where we have specific ranges. So we only want frequencies from this range to this range to be filtered through, or we don't want frequencies from this range to this range. And this is how your car stereos work. So they actually dial into a specific frequency, plus or minus, I want to say 3 or 4,000 hertz or something like that. 300 hertz, something, whatever it may be. They actually dial in and filter out everything else except for what that specific frequency. So that's kind of the idea here is this is going to be how your radios work. Okay, so pretty cool. First semester, we're already learning how to manipulate radios. So anyway, without further ado, it's kind of a long intro, but let's get on to this. So we're going to start with topic 4 with filters. So the first thing that we have, and we need to know, what is an electronic filter? I've kind of already talked about it, but let's just get some of these definitions written down. Electronic filter. So it's used to separate the output signals based on their signal strength, based on their frequency. So used to separate output signals based on their signal strength which is also based on their frequency. And so one of the things that we need to remember, so that's kind of the idea with the filter is electronically we're using these signals. That's the key, is we're using the different components, resistors, capacitors, inductors, things like that, to be able to get all those ready to go. So those are used to separate our output signals based on their signal strength. We're going to attenuate them up or down depending on what they are. And the basis of this is it's based off of um, the power, the heating effect that we have on each of these guys. So remember, when we have an AC signal like this, we have our peak values here, This would be our negative peak when it goes into the negative cycle. But we have this value that sits right here. This is 0.707. This is the DC equivalent. This is what we use to determine power. So like what we've been before with all of our calculations and everything, when we're solving for power, we want everything in terms of RMS power because that's the DC equivalent, and that's just so we can compare apples to apples, and specifically Gala apples to Gala apples instead of trying to compare a Honeycrisp to a Fuji, which Fuji suck, but that's another topic. So basically what it is we're kind of comparing everything in this. We're using this comparison, this 0.707 value to solve for these things. And this will become a little bit more apparent when we talk about this in a little bit. So kind of the idea here is anything that we want to use later on, as long as it's higher than a certain value, will get amplified. If it's not, it won't. That's one of the cool things is all these things kind of feed together. So this one is going to filter out our signals, and it's going to attenuate signals. It's going to drop them well below their normal peak values, so that when we go into to an amplifier, as long as it's a value over a certain level, then it'll get amplified. If it won't, it'll just get ignored. And that's one of the kind of the cool things that we have with amplifiers, just kind of as a precursor for you guys, is if your signal strength isn't above a certain value, voltage or percentage, things like that, the circuit won't even do anything with it. It'll just flat out ignore it. So this is how we create those signals, is we actually attenuate the signals away and down from the max voltage, so that way they don't get picked up later on. And that's kind of where this is all coming from. So the next term that we have, so we have our electronic filter. The next we have is a decade. And again, my pen shut off, so we got a decade. So basically when we go up and down a decade, think of it in terms of our frequency. This is equal to 10 times of a frequency. So if we go up a decade, that means we multiply our frequency by 10. If we go down a decade, we divide our frequency by 10. So that's one of the terms that we're going to use. The next one we're going to use is an octave. Now an octave, basically what this means, we're doubling the frequency. So when we double it, so if we start at 1 kilohertz and we want to go up an octave, we're going to go up to 2K. We double it again, we're going to go to 4K. We double it again, we're going to go to 8K. So, as we go up and up, we're going to see these frequency changes. And this is how we're going to reference a lot of them in our filters, is we want to look up and down, plus and minus a decade or two or an octave or two, just to kind of get an idea of what's going on with our filter. And that's kind of how the rest of the charts are going to be set up, is we're going to be going up and down, doubling. To some extent, sometimes we're going to go to the extremes and just see that, hey, when we get up to this frequency, we're going to have no signal, or we have all the signal. It doesn't matter what we have at this point. It's going to be maxed out. So just kind of remember these. Decade is you go up and down 10 times of a frequency. The octave, you go up and down 2 times of a frequency. One of the next terms that we have to understand is a critical frequency. So our critical frequency, and this is designated by an F with a subscript of C on it. Okay, just so remember, F is our frequency, and then the little c just tells us this is our critical frequency. So what this is this is the frequency at which our reactance value is equal to our resistance value. This is also called the half power point. Also called the half power point. It's called the -3 dB point. So one thing that we're here is when we're at this frequency, since these guys are equal, one thing to remember here, our current, the angle of the current is going to be equal to 45 degrees, which we should know is from some of the examples and from some of the labs that we've been doing, that as our x of c or x of L is equal to r, we're going to see that this 45 value appears. And it still is maintained through these guys as well. So it's going to be plus or minus 45 degrees, depending on if we're using capacitors or inductors. like we've seen in the lab. So the big thing is your critical frequency is at what frequency does your X equal your R. So when those guys are equal, you're also going to get your most amount of current. You're also going to get the maximum power transferred back and forth, because it gives you the best ratios for it. So one thing to remember. We're going to be playing with this a lot. Is our critical frequency. What is our critical frequency? Finding a critical frequency. How do we manipulate things if we change components, things like that. So we start off with that. Come on. I think it might be time for me to get some new batteries for my, there we go, for my pen. All right, so we have our critical frequency. The next that we're going to talk about decibels. Now a decibel is just simply a ratio between our input and our output. Now this is its symbol, so a little d and a capital B. You'll see this a lot in sound and audio and things like that, but we use it here too because, like I said, it's just the relationship between our input and output signals. So relationship between output and input. So we have two formulas that we can use for it depending on what unit we have. So we can use either 10 log of our power out over the power in, or we use 20 log of the voltage out over the voltage in. Now that's going to give us some value in terms of dBs. So for what we're going to be talking about here is we're pretty much going to have a loss, or we're going to break even. We're never going to gain because we're not amplifying anything. We're just filtering things out and we're attenuating it. So the idea here is, so like before when this says, hey, we have a negative 3 dB point, 3 decibel point. So what this means is we've gone down, we're losing 3 decibels of our output compared to our input. So this also represents 0.707 of our volts peak. Okay, so this is where this all comes along. This is why this is the negative 3D point. Because if you were to take, your RMS values, things like that, you can solve through these. This 0.707 is going to show up all over the place. So the idea behind this is we want to know how good our system is. How good is it knocking things out? Are we locking things out 2 dB? Are we locking things out 5 dB? For those of you that do know a little bit about sound and audio and things like that, when we talk about gains, usually those are positive because we're amplifying the sounds. With mixer boards that have a whole range of frequencies you can do, and you can kind of set those up as you like, it's the same thing. We're amplifying specific frequencies, and we can adjust those frequencies on those boards and set everything up so we can filter out exactly how we want our music to sound, how we don't want it to sound, things like that. Audio is honestly one of the easiest examples to use to kind of explain this decibels. It's all over the place. And that's why when you increase your number of dBs or increase the power on your knobs, you're going to see the volume go up, because that's what we're doing, is we're increasing our voltage out compared to the voltage that we're putting in. Won't get too much into that because that's what you guys are going to cover next semester. But like I said, this is the relationship between how much output and input signals that we are. And so if it's a positive dB, that means we've amplified. If it's a negative dB, it means we've attenuated the signal somewhere. The next one that we have is our resonant frequency. So our resonant frequency, this is designated with the F and a lowercase r underneath. And what this is the frequency at where our reactance for our capacitor equals the reactance for the inductor. So this is slightly different than the critical frequency, because that just gives us 1 point. This is when we're talking about capacitors and inductors, and that's why these guys are a little bit more complicated when we get into them, is because they have inductors, capacitors, and resistors. So now we're going to be talking about RLC circuits, whereas previously, especially like with the critical frequency, we're only talking about RL or RC circuits, not all three of them combined. So now we have to start worrying about it when we get into these, and we'll talk about that in one of the later videos for the week. But anyways, we have our resonant frequency. So when we're at our resonant frequency, some of the cool things that happen, our current has an angle of 0 degrees. Because when these guys are equal, remember, this is a minus J value, this is a plus J value. So for example, if we had 500 ohms of reactance for both of these guys, we would have a plus or a minus J 500, and then we'd have a positive J of 500. And remember, that's just in relation to their phase. So, but when in this case, we end up with a net reactance of 0. So they actually cancel each other out. But there is a little bit of amplification that goes on there. If you were to measure these guys individually, you'd see some crazy high voltages, but you're going to see equal and opposite. So they're going to completely cancel each other out, and then you're not actually going to see anything across those guys. So that's one of the cool things. And then also, at our resonant frequency, our impedance total is at a minimum. So when our impedance is at a minimum, remember the inverse relationship we have between impedance and current, our current is going to be maximum. So then as we start shifting things, we're going to start seeing our current change, we'll start seeing our impedance changes. But this is kind of the cool things that happens is when we're at resonance, our X of C and X of L values are equal, so they cancel each other out. We're left with a 0 degree phase shift, which is really nice for measuring on our scope. And then, like I said, we have a minimum impedance and we have a maximum current. So it kind of gives us the best of both worlds when they're at resonance. And the reason we want them at resonance is, again, is because we're trying to filter out specific frequencies. That's kind of the whole idea behind this. These guys are actually really cool. They're kind of complicated at first, but they are really cool once we get going into them. All right. So that's kind of the big idea for the terms. Just to kind of go through. We'll go through some more as we are talking about it, but primarily that's what I wanted to talk about with the terms. Okay, so what kind of getting back to what is filtering. So filtering attenuates a signal in a variety of possibilities depending on how we want it to work. So based on circuit configuration, and those are the possibilities we have. So some of the things we can do is when we're looking at a filter, and we'll talk about these exactly about what kinds they are, but when we're looking at a Bode plot of a filter, so basically we're gonna chart the response curve that we have. So when we look at it, our x-axis is going to be our frequency, with starting at 0 hertz and getting up to we'll just say 20 meg for right now. We're probably not going to get much over that. The generators that we have won't do those 20 meg ones. Even the nice ones we have at school struggle getting up in the upper megahertz ranges. We do have some in RF that actually get into the gigahertz. Just kind of to show some of the things that are going on there. But anyway, so we have our frequency and then we have our amplitude on this side. And most of the time we're measuring this in volts. So we have from 0 volts to whatever our max voltage is, for example. Now, one of the things we need to look at is we'll have a curve that's going to go like this based on what type of filter we have. So it's going to look like that, or it could look like this. So let's kind of understand what's going on with this. So this right here, this is our output. So this is depending on what we're doing. So as we get higher in frequency in this one, so as we get higher and higher in frequency, we get higher and higher voltage until eventually we max out at our max VP, and we just kind of stay that way forever. On this guy, we're starting out at our high voltage, and then as we increase frequency, we're decreasing our voltage. So eventually it rolls off to where it attenuates. Well, right here at this point, when we have kind of the curve, and I kind of drew these a little bit off scale. But what this point gives us is some information. So this point right here on our curve, this is our critical frequency location. So right here, this tells us what our critical frequency is. This is when we have 0.707 volts, negative 3 dB. This is what it looks like. So now that we've created this, we have this critical frequency. So now what's going to happen is if we go, for example, in this first circuit, this first waveform, if we go lower, anything in the low end is going to attenuate the crap out of our signal. No matter what we put in, it's going to drop it by 0.707 or less. And especially when we're starting out, we're going to get almost nothing, and then it's going to kind of climb up a little bit and then flatline. So this area over here, this is our reject area. And we call it reject is because those are the frequencies that we don't want. So we're attenuating them out and we're rejecting them because they're less than our 0.707 value, our negative 3D point. So anything lower than that on our amplitude, we don't want. Anything above our critical frequency, this is what we call our pass region. Okay, so we have our V out, we have our critical frequency, we have the area of frequencies that we want to reject. So this means anything in this region right here, we're going to reject. And anything in this region, we want our circuit to pass. And we don't want it to change it or attenuate it at all. There'll be a little bit of attenuation here, but not much, at least not much to make a difference. And then as the farther it gets out, it just, gets up to the maximum voltage and goes on forever. So we have our pass region, we have our reject region. We have our frequency range down here at the bottom, which is our x-axis, and we have our amplitude or our voltage range, which is our y-axis. So in this instance, if we were to look at this, we want to name this filter, so that way we can kind of reference it again. So in this instance, we have a circuit that is passing high frequencies and is rejecting low frequencies. So looking at that type of a waveform, we can say that this filter is a high pass filter. Okay, we're allowing frequencies at a higher range to go through without us doing anything to it. Anything in the low end we don't want, so they get attenuated. This other filter, or this other waveform we look, again, we have our V out, we have our critical frequency, and this is also at 0.707 volts. We have our amplitude, we have our frequency. So in here, anything that's above this imaginary 0.707 line, anything above it is the stuff that we want. So this is going to be our pass region. Basically, we're passing those frequencies through our filter without doing anything to them. And then this is our reject region. And that should be a J, not a G, I apologize. So again, anything over this critical frequency, we're going to reject, and basically we're going to attenuate the crap out of. And then anything below that frequency, we want to keep, and we want to leave it alone as much as possible. So in this case, we have low frequencies we're passing through, high frequencies we're rejecting. So in this case, this is a low pass filter. So it doesn't matter the configuration that we put in our components, all high pass filters are going to have a similar waveform. The only difference is going to be where its critical frequency is, and that's the biggest difference that we have to do. But they're all going to look pretty much that exact same. They're all going to have the same curve. The higher the frequency, the closer it gets to the max voltage, till eventually it's just the max voltage, no matter how much higher you get. Okay, low pass filters are going to work the opposite. Anything lower than the critical frequency is going to be up at the max value, and anything that starts to drop off at that point is going to be rejected, essentially what we call rejected. So now that we have kind of understanding here, so this is our high pass filter, this is our low pass filter. I'm going to talk briefly about the other two types of filters that we have, but like I said, we're going to talk about them later when we get into the resonance, but just so you're aware of what they are. So now that we have, come on. Just let me write it. Apparently my batteries are really dead, so I apologize. I'll get some new batteries and get this problem fixed before we move on, before it gets too late in the week. I just need this thing to work. Come on, just work for 10 more minutes. I promise, then I'll be done. There we go. Finally. All right, so we have a high pass filter, we have a low pass filter. The next type of filter that we're going to have is going to look like this. This is a band pass. And this is going to be a band stop. So when we look at these, so this is our pass region, this is reject, this is also reject. We have now a critical frequency for our low end. We have a critical frequency for our high end. Again, on the band stop, we have an area for where it starts, where it stops. This is going to be our reject region, and this is our pass region. And so really, these band pass, band stop filters, these are just combinations of our high pass, low pass. So we're going to put up a high pass filter at some point down here on this end, and then once we get through here, we're going to see, we're going to stop, we're going to put in a low pass filter so it starts cutting it off. So they're just combinations of these different types of filters. But like I said, we'll talk about that in our next step. So again, high pass passes any frequencies above our critical frequency, and that critical frequency is designated as the 0.707 of our max peak voltage. So we'll put that in there. And our low pass passes anything below our critical frequency, which is anything that has a voltage higher than our 0.707. And then our band pass, band stop, they have a frequency range that they will run between, and and we'll figure out how those are controlled. So it has two critical frequencies, a high and a low, and then the band stop rejects in a specific frequency. So like I said, we'll talk about all those here in a little bit in the next video or two. I just want to get you an idea of this is what is going on. Okay, so as we get started with these, things to remember. Things to remember. Buy new batteries for your pen. And then maybe it will work when you need it to. Okay, now this is just getting ridiculous. I do apologize, guys, for this. There we go. Okay, things to remember. The capacitive reactance formula is equal to 1 over 2 pi times the frequency times the capacitance. The capacitive inductance is equal to 2 pi times our frequency times the inductance. So remember that as frequency goes up, our X of C goes down. As frequency goes up, the X of L, inductive reactance, goes up. To find our critical frequency, that is going to be at a point where our resistance equals the reactance. And at resonance, we find that when our X of L is equal to X of C. And then we have formulas for decibels. So 10 log is our power out over our power in, or 20 log of the voltage out over the voltage in. And finally, our critical frequency is at a point where we call it -3 dB, the half power point, or it's 0.707 of the max voltage. Okay, with that, I'm going to go ahead and end this video for the introduction, and I will go find a new battery for my pen and kind of go from there. And then we'll start in with how to actually build these filters. And so we're going to go through RC filters first, and then we're going to go through RL filters. And then once we are done with those, after that, we'll start into the series resonance, which is RLC circuits. All right, guys, we'll see you in the next video as soon as I get everything changed over.